because I don't have his presentation. So
More time for us.
yeah.
That's true. That's true. Let's see. So we start having people coming through. We are recording. So hello everyone and welcome to another webinar. Please introduce yourself on the chat window and we will be starting in about 10-15 minutes. Thank you. I should use my chat. There we go. Zoom webinar chat. Hello, Bert, Nebraska. Oh, hi, Gary from England. Good to see you. So today we have a really pretty day here. How are you guys doing? Fred, how is it in Long Island?
It's chilly.
Is it?
It's the upper 60s, maybe it's 70 degrees today. It's wonderful. It's like the first day I've been really comfortable in months.
Yeah.
I went for a bike ride this morning. I had to put a jacket on.
Oh, wow. That's not happening in Florida yet.
No.
How's your weather there at this time of the year?
Yeah, hot, rainy. Yeah, the telescope is pretty much shut down for the summer. And right now we have a tropical storm just south of us. I'm going to be driving to South Florida as soon as this is over. So help my daughter move into college. So I drive right into the tropical storm. It's windy enough up here right now. It's worse down there, rainy.
Oh, wow. So we have people coming from Belgium, from Massachusetts, Kentucky, Germany, England, India. Hi, India, 11:22 p.m. Welcome. Thank you for joining us. Quebec. Oh, it's really cool to see people coming in. Brazil. Hi, Ale. Oh, that's really cool. Argentina. Josh, hi, good to see you. Hi, Africa. Belgium, Turkey, Greece. Καλησπέρα, Ελλάδα. Και καλησπέρα στην Κύπρο μας. Arizona, Argentina. The gang is here. Nice. US. We've been having plenty of Nova lately. It's like when it rains, it pours. It's like a competition. Which constellation is going to have the most? Really exciting, actually.
I really haven't been paying attention this year because CTIO is still shut down because of the virus.
Oh, yeah.
So I'm trying to dig into old data, get something published.
But you know, the cool thing is that although professional observatories are closed, our observers are open for business.
That's right.
There you go.
Yeah, Nova Reticulum would have been wonderful for Chiron because it's still like 8th magnitude, I understand.
Is it still?
That's the last I heard.
So we need to keep it on our lists.
By the way, you guys should keep watching SS Cygni. The X-ray people have noticed it's been getting brighter for the last few years. Maybe it's about to explode. Who knows?
We just got an alert yesterday.
Yeah.
I saw a note on that too.
Yeah. That'll be
Even
interesting.
that well-behaved system acting up. You never know.
Mhm.
Is there such a thing as a well-behaved seaweed?
Well, relatively speaking.
Yeah. Let's see. So we have people coming in from Arizona, the UK, Illinois, New Zealand, Bulgaria, Australia. Get better soon, Gary. Around here. Wow, nice. Clear but hazy in the UK. We're having a really nice weather here. My heart goes out to all our observers and friends on the West Coast, though, because the fires there are going insane. And it's heartbreaking to see it. All right. Northern California. Hi, Pamela. How are you doing? Happy birthday to Michael Poxon. We have a special Cataclysmic cake for you today.
And we scheduled a webinar just for your birthday.
We scheduled it. Namaste, India. North Carolina. Oh. Cape Town. Oh, that's very nice. So we're going to have like a quiz at the very end of the presentations, right? What is the system right behind us? So SS Cygni is right behind me. Sean?
I have RS Afiyuki going into Nova Outburst.
Very nice. It's going to be a question afterwards. I hope you guys are paying attention. Hi, Ron. Hi, Chile. Hola. Florida, Brazil, Ireland.
Hope you're not in South Florida getting the tropical storm moving through. It's windy enough up here in Orlando area. Yeah, see a lot of very familiar names on the list.
I'm going to start in about 5 minutes. We have more than 100 participants at this point. But people will be coming.
Oh yeah, I'm Robert. I'm in Claremont, west side of Orlando then.
Hi, Rod. Good to see you. What time is in Australia right now? Four a.m. Oh my goodness, are you? So Rod Stubbings, one of our very prolific visual observers, most likely he's keeping us company.
It must be cloudy if he's not out at the telescope at 4 a.m.
Oh dear. Missouri, Canada, US, Belgium, Cordova. It is cloudy. Oh, I'm so sorry,
I know
Rod.
it. Yeah.
Venus, Florida. Okay. I didn't know that Florida had a Venus.
It just feels like it every time you go out, night or day.
Hello to Lima, Peru, London, Spain. Welcome, welcome. It's wonderful to see you all here. Wow. Cloudy. Smoky, Arizona. Hi, Sumner. How are you? Good to see you. Cool. Santa Monica, California. How is California right now? They're waking up with an orange sun every day. I saw pictures, they're kind of devastating.
Yeah,
Smoky.
gotta play havoc with your transformation coefficients, right?
If you can open your telescope.
Yeah, no, I think, yeah, it's safe to,
Yeah.
definitely not.
Hello to Barbados. So wonderful to see you. Thank you for joining us. Media video closed.
Oh, that looks pretty awful there, Mount Wilson.
Looks like pictures of Venus,
And it does, and much more so than Orlando.
except for the domes.
Yeah. Yeah, trees probably are a little more thick there and then on
Yeah.
Venus too. Yeah, Portland also getting a lot of fires.
Hello, Brazil, Germany, England, Houston, Ohio, Mount Will. Yeah, I saw actually Maine. Hi, Maine. I'm just waving from Massachusetts. I hope you guys are enjoying the nice weather we have here as well. North Carolina, New Mexico, Texas. Michigan's here. Madrid, Spain. Very nice. We'll wait just one more minute. We are more than 170 participants at this point. Hello, Berkeley. Be safe. Hi, Pat in San Diego. Stay safe, please. My goodness. Hi, Jeff. Good to see you. All right. Are we ready to get started? I think we are. Good morning, good afternoon, good evening, everyone. My name is Stella Kafka. I'm the Executive Director of the AAVSO, and it is a great pleasure to introduce another webinar of our series. Today, I am joined by Sean Borek, Fred Walter, Patrick Schmier, and we're waiting for Joe Patterson to join us. And we are going to discuss cataclysmic variables and some of the most explosive and unpredictable phenomena in our universe. This seminar series, this webinar series wouldn't be possible without the help and support of our sponsors. I would like to acknowledge and thank Boyce Research Initiative and Education Foundation that provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals like the Journal of the AAVSO. And also I would like to thank ATI Cameras that are manufacturing a diverse range of quality astrophotography cameras and accessories, along with a range of free software to help you maximize the output of your equipment. For your information, please visit their webpage for all kinds of goodies there. I would like to start with a couple of housekeeping details. At the very bottom of your screen, you will see a menu with two important windows. One is the chat, and I would like to encourage you to actually go there, introduce yourselves, tell us where you're from. And the other one says Q&A. This is where we're going to be discussing questions. You can actually ask questions during the presentations if you want to. We will address all questions after the presentations. Feel free to ask anytime. And if we don't get to any of your questions, please feel free to go to the observing sections forums and ask your questions there, and somebody's going to get back and answer for you. And we can continue the discussion there on forums. Also, down here, you see a little button that looks like a microphone. If you click on that, you will get to a drop-down menu that provides selections which control your audio settings. If you have any issues with your audio, please look at those settings. We cannot fix them from here. This is something for you. So at this point, I'm going to stop sharing my screen and welcome Sean Dvorak. Hi, Joe. Good to see you.
Hi.
Who's going to get us started? Sean's all yours.
All righty. Welcome, everybody. Stella's already given all the introductions, and it was very exciting to see all of the people that are in. We were up to 188 participants now from all over the world, especially folks who are, it's middle of the night. They're in probably India and Australia. So thank you for joining in. I'll apologize in advance too. Allergies here are terrible, and lots of pollen in the air. Everything's covered in yellow, and my throat is really sore. So I'm kind of gravelly and may not be so clear. So I'll try to enunciate clearly. Go ahead and share. Hopefully I am on the right page. So the title of my talk is the Cataclysmic Variable Bestiary, your field guide to cataclysmic variables in the wild. We're going to talk about a lot of different types of cataclysmic variables here, and like Stella said, there are many different types, and they're all cataclysmic in the name. You get the idea that they're very energetic and unpredictable types of objects. So a little bit of background. I'm sure a lot of this will be old hat for some of you, but just a little bit of groundwork. Cataclysmic variables really were the first recognized variable star type, even though they had no idea what it was, of course. As far back as written history goes, we have records of these new stars, or nova in Latin, that have appeared in the sky. Ancients considered the heavens to be fixed. The sun and moon and planets are moving around, but then very well predictable patterns. And the stars were seen to be just fixed lights, perhaps in this dome over the earth. And so when a new star suddenly appeared, possibly a very bright star, it was very puzzling. And as you can imagine, it was considered to be an omen, either for good or ill. And that's pretty much where the science of cataclysmic variables stayed for millennia. In 1855, astronomer Hind discovered a new star through his telescope. And he obviously knew what this was. It was a nova. There hadn't been a star there before, and it had suddenly appeared and then disappeared. However, it became clear after a few months of observing that the same star kept reappearing and just as quickly disappearing. So this was obviously something new. Still didn't have any idea what was going on, but it seemed like a nova, only a smaller outburst. Didn't get that bright. You couldn't see it except through a telescope. So dwarf nova seemed like a reasonable name for it. Understanding progressed very slowly, like all things in science, incremental growth. The photographic surveys starting in the early 20th century turned up a lot more of these dwarf novae. It was easy to spot them on photographic plates appearing and then disappearing repeatedly. New instrumentation helped uncover some of the information about these objects, and eventually we realized that the spectroscopic signatures of novae and dwarf novae were different, and the novae that they were observing through large telescopes in these nebulae that they thought at the time, actually galaxies, those turned out to be different still, and today we know those to be supernovae, another type of cataclysmic variable. However, they all acted in a similar fashion, rapidly brightening and then fading away more slowly. And so it's understandable that they considered them to be related types of objects. So cataclysmic variables, at the 100 light year view through your telescope, the most significant part of this is that cataclysmic variables increase in brightness very quickly. And depending on the type, you get very small increases or incredibly large increases. And how long they stay bright also varies between these different types. But cataclysmic is in the name, and that's really talking about the light curve, although the physics going on in the system is also quite cataclysmic now that we have some understanding of what's going on there. Cataclysmic variables are divided into a lot of top-level categories and subtypes underneath them. There have been many, many different types of cataclysmic variables throughout the years, and initially that was just based on what does the light curve look like, how is it behaving, and because that's all the data we had. And as we had spectroscopy, we understood that there was some significant differences between these types and helped break those up or make sure show that they were separate. But in a lot of cases, those types really were just on a continuum. They weren't distinct, and so from other types. And so some of those classifications have faded away, but we have a pretty good grasp, we think, now. Most types of cataclysmic variables share a few common physical design features. Again, most of them are binary star systems, and in this system, one or even both of the components are degenerate. They're compact objects where gravity has crushed the matter down to a incredibly dense state, and so they're nothing like an ordinary star. They're not fusing matter anymore. They're dead, basically. And we also see in these systems mass transfer, where this immense gravity of this compact object is pulling matter off of its companion, and it gradually accumulates eventually on this compact object. So the top level categories, maybe, if you will, of our cataclysmic variable beasts are dwarf novae you're talking about. And here, this is a binary system. The compact object is a white dwarf, a star the size of the Earth, but maybe the mass of somewhere around the mass of the sun, and a relatively normal star. And they're in this close orbit. Typically, this orbital period is measured in hours, 3, 4, 5 hours. That's pretty typical. And because they're so close, we have this mass transfer where the gravity is pulling matter off of this dwarf star. Symbiotic systems, again, that's very much like a dwarf novae, but you swap out the dwarf for a much larger star, a giant or a subgiant. Because that star is so big, you can't get it into this tiny little 3-hour orbit, so the orbital periods here tend to be much larger, many, many hours and over to many, many days. X-ray binaries. Here's a great example of new instrumentation, discovering new classes of objects. Until we had the technology to launch X-ray telescopes into space, or at least float them very high in the atmosphere, above the atmosphere that blocks the X-rays. We didn't know these existed, and neutron stars and black holes are what's forming the compact object in place of the white dwarf of these. And so you get the much more intense gravitational field of these larger objects produce more extreme physical conditions. And so these are bright in X-ray, whereas dwarf novae are not as energetic and tend to have a lot of light, primarily in visual and ultraviolet. Novae, if you look at a nova before it erupts, it's probably going to look pretty much just like a dwarf nova. You have this white dwarf, typically a rather massive white dwarf, on the high end of the weight scale, and a companion, either a red dwarf or a subgiant in orbit, and there's matter being funneled. What happens here, though, is the nova is much bigger explosion, much greater range. Dwarf novae are 3 to 4 magnitudes, so 15 to say 40 times increase in brightness when it goes into outburst. An eruption in a nova system is maybe 10 magnitudes, and the difference is the actual physical process that's going on. What's happening in the system to cause this brightness spike is considerably different between novae and dwarf novae. Finally, supernovae. Everybody's heard of that and understands that this is like the comes by the name super in its name very honestly. It is an incredibly violent explosion, so much so that it often destroys the system. We don't have any recurrent supernovae, most likely, since it's a very violent event. So a little more detail on the dwarf novae types. Again, this is a white dwarf pulling matter off of a companion star, and the matter can't fall directly onto the white dwarf as it falls down this really steep gravity well because of its angular momentum. It's in a stable orbit when it's on the red dwarf, so it has all this orbital momentum plus the additional velocity as it falls down towards the white dwarf. So initially, this matter whips around the white dwarf and goes into a very elliptical orbit, but gradually that orbit becomes circularized as it collides with the other gas that's already in this disk. I term this thing the accretion disk because it's accreting matter from the red dwarf, and then it accretes onto the surface of the white dwarf over time. And this has been one of the useful developments or big developments in studying of dwarf novae is the realization that this disk has two different states. The quiescent state, when it's at its low brightness level, the disk is slowly heating. It's accumulating matter because, again, the matter can't fall out of that inner edge of the disk very quickly because it's conserving angular momentum. It's going very quickly. It can't just fall onto the surface of the disk any more than a satellite in orbit around the Earth can just drop straight out of the sky to the surface. It's got to fire a retro rocket in that instance. So the matter has to be able to slow down somehow. So it's just in orbit around it in this accretion disk, and gradually growing and growing because it's getting matter off of the white dwarf the red dwarf all of the time. And eventually, though, that disk gets hot enough that it switches to a high viscosity state. And you can think of viscosity as how sticky is the matter in that disk. And when it is in this high viscosity state, the very rapidly moving matter at the very inner edge of the disk, again, because it's closer to the white dwarf, so it has to go faster, it can transfer some of that momentum to the next, the particles that are just outside of it that are going slightly slower in their more distant orbit. And that works its way all the way through the disk. So the whole disk kind of spins up, but the matter closer into the star is able to slow down and eventually can fall onto the surface of the white dwarf. So now we have this rate of draining out of the disk is much faster than what it's accumulating off of the red dwarf. And so we go into this outburst state where the disk is very hot. All of that momentum is being converted into heat and light. And so the disk drains in this high viscosity state until it cools enough the switch flips back to the low viscosity, slowly heating state. And we do it all over again then as the disk gradually grows. You see these outbursts, and it's just flipping back and forth between those two states. Really quite cool physics going on there. It kind of has a echo of a resemblance to how pulsating stars like Cepheids and Delta Scuti stars work, because we have this ionization layer inside those stars that alternately become opaque and transparent, and that's similar to the effect that's going on here, but in this disk of matter around a white dwarf. Typically white dwarf novae have a range of 3 to 4 magnitudes between low and high states, and as you can imagine from the physics going on here with this disk switching states, it's a very dependent how bright the outbursts are and how frequent they are very dependent on the orbital parameters. How close are these stars? What's their masses? How hot are they? Which all affect how quickly the matter can be pulled off of the red dwarf, and then so a faster mass transfer may mean this grows faster and flips into that high outburst state more quickly, so you get more rapid outbursts. So that by observing outbursts, we can kind of get an idea of what's going on in this mass transfer in the system. So there's a number of subtypes of dwarf novae. There are a lot of these stars. They're not very bright intrinsically, not like a nova or a supernova, So we can't see them a great distance away from the Earth, but we still see a huge number of these objects, and every day they find more in these automated surveys. So we know that the space density is fairly high on these things. SS Cygni stars. This is the, if you will, the most regular of these irregular cataclysmic systems. The outbursts are on a pretty regular basis, and they're generally pretty similar to each other, which gives you the hint that that state flipping for that disk, the accretion disk, is probably pretty regular. The mass transfer rate's probably pretty regular. It's in a pretty stable state. There's a nice equilibrium going on there between the mass transfer rates. So they're well behaved for cataclysmics, I guess, the way you'd be able to quantify it. And so light curve on that. Here's our friend SS Cygni. This is a short segment in a simply amazing data set that the AVSO has got, stretching back about 130 years and something like 600,000 observations. So a lot of observers have been very busy observing this star. It's well placed, it's bright, it's popular, easy to observe, which is great. You can get, after 130 years, we at least have some ideas of, longish term behavior. It's still not, anything in terms of the lifespan of the system, but, we've got a lot of data on it. And even if you look at this light curve, which is a pretty typical segment of it, the spikes are fairly regular in time. However, we've got some of these that are definitely wider. This guy here is substantially wider, stayed in outburst a bit longer than some of these that, as soon as it reached outburst, it immediately started to fade. And then we've got this little runt here. It's like the star just decided, no, I'm not going to go into outburst. I'm going to instead kind of go back to this not quite totally quiescent state here. It's a little elevated magnitude, and then go into this big outburst here again. And then again, we're in this kind of elevated state. So even SS Cygni is doing odd things from time to time. So it never hurts to keep an eye on even this kind of object that's well observed. The next type of dwarf novae, what I would call the super stars, not supernovae, but super white dwarf or super dwarf novae. SU Ursa Majoris, ER Ursa Majoris, WZ Sagittae stars. There's several classes here that are related, behave similarly. They have these super outbursts where it'll have normal SS Cygni type of behavior. And then occasionally it will have a super outburst, which is 2 to 3 times brighter and lasts substantially longer. And one theory is that the disk, because of the orbital parameters and the mass transfer rates and basically the exact structure of the system, the disk doesn't fully drain during outbursts, and so the matter builds up over time, and so the disk gets bigger and bigger until it finally gets to the point where it has this super outburst where there's a lot of matter. It takes a longer for it to drain, so the outburst lasts longer and is brighter because there's more mass in the disk itself. Interestingly, these systems tend to have fairly small orbits, short orbital periods, and because the disk is so large, it can get into an orbital resonance, like a 3-to-1, say, ratio of orbital period with the companion. And just like Saturn, the gaps in Saturn's rings being caused by resonance patterns with its moons, this causes a warp to develop in that disk. And so it'll form an elliptical shape, get kind of bent out of shape and maybe a tilt to it. And you can actually see that effect in the light curve. You get these little wiggles superimposed on top of the outburst, termed super humps. And basically they track the orbital period of the matter as it goes around the star. And from that, we can get very interesting information about the relative masses of the stars in the system. And it's a way to get more exact measurements where we only have rough ideas, a lot of these numbers for many systems. So again, light curve, we'll again pick on one of the namesakes of one of the classes, SU Ursa Majoris light curve. Here's our super outburst. You can see it spends a lot of time pretty bright, gradually fading, and then starts to drop like rapidly here, like in a normal outburst. Then we get this little echo. Typically we see an echo outburst here, and then more normal outbursts. And I'm moving my mouse on the wrong screen, so this is what I was gesturing, super outbursts here, and then these smaller outbursts following. And this train of regular outbursts may go on for weeks, months, until another super outburst occurs. And again, it's not terribly predictable. They're somewhat periodic, but basically you just never know. So you have to keep an eye on them. What I would call the sticky stars, not a technical term. These are dwarf novae that tend to get stuck in one state or the other. Z camelopardalis stars are quite interesting in that they look like an SS Cygni type star, very regular outbursts, pretty, looks run of the mill. And then suddenly it just gets stuck, goes into outburst, and then never falls back to its low state. And it stays maybe 2/3, 3/4 of the way into the maximum brightness. And it can do that for days, weeks, months even. And again, you just never know when it's going to happen, when it's going to end. And again, because they look like SS Cygni stars most of the time, except when they have this standstill, there's an opportunity for monitoring some SS Cygni type stars, and it takes fairly dense coverage to be able to pick up a few nights where it may be at this intermediate magnitude where it's in a standstill. So it requires good coverage, but there are probably quite a few stars classified as SS Cygni that probably show Z camelopardalis style standstills from time to time. Here's a nice light curve. Again, Z cam itself. Here's our nice SS Cygni type, regular outburst, just a regular old dwarf nova, and then it just forgot to go back into quiescent state here after that last outburst. And here we've got about 200 days of constant brightness where it's stuck, and it actually goes on a bit beyond this. And really it's anybody's guess when it will stop, anybody's guess when it starts. So these are very unpredictable. Intermediate polars and polars. So these are systems, dwarf novae with very intense magnetic fields. Stars typically have a magnetic field. Some of them have very strong magnetic fields depending on exactly what's going on in the star, but these have ridiculously powerful magnetic fields. For reference, the sun's magnetic field is about 1 Gauss in strength, which is about twice the Earth's magnetic field. And on intermediate polars, the DQ Hercules stars, that magnetic field is maybe 1,000,000 Gauss. And it's so powerful that it can overcome that angular momentum that's keeping the matter from falling directly onto the white dwarf. And it will pull the matter out of the accretion disk, then down onto the magnetic poles of the star in these columns of super hot matter. And so what happens, the accretion disk, the inner edge of it is getting eroded away by these magnetic fields, and the mass transfer onto the white dwarf itself maybe is somewhat higher than in a non-magnetic system. Polars, AM Hercules type stars. Here, we take that, 1,000,000 sounded like a lot of, 1,000,000 Gauss sounded like a pretty powerful field, but here we're 100 or even 1,000 times stronger still. And the magnetic field here is so strong that we don't get any accretion disk at all. It simply, as soon as the matter stream gets close enough to the star, then the magnetic field grabs it and funnels it right down to the white dwarf's magnetic poles. And since they say, picture's worth 1,000 words, blah, blah, blah. Here is an artist's rendition of an intermediate polar. Again, like most are like dwarf novae, other dwarf novae, we've got our red dwarf secondary here. We've got the stream of matter being funneled down onto the accretion disk. And we've got here, though, the magnetic poles oriented this way, and a bit of a tilt from the orbital plane of the system. And its magnetic field are pulling that matter right off the inner edge of this accretion disk. Now, if this was a non-magnetic dwarf Novae system, this accretion disk here, there wouldn't be this gap. It would be extending nearly down to the surface of the white dwarf itself, depending on the state of the disk. But here, all of this empty space is being swept up by the magnetic field. And here, here's a polar system with its even more intense magnetic fields, and there's just no accretion disk there at all, right? It kind of tries to maybe form, but the magnetic field just grabs that charged matter and funnels it right onto the star. Now, because there's, an intermediate polars that has a very small or reduced size accretion disk, and in polars there's really no accretion disk, you typically, see weak and infrequent outbursts in intermediate polars, and very, uncommon to see an outburst in a polar system because there's just no disk there to form that outburst state. What we do see, though, in these types of stars, that these columns of matter, as they fall down onto the magnetic poles, they have quite a lot of gravitational energy. And so when they strike the surface, they heat up the already incredibly hot surface of that white dwarf. So we get these two hot spots, one at each pole. And as the white dwarf rotates, oftentimes in a matter of minutes, they're very fast spinning objects, these hot spots come into view and out of view, and you can actually see that effect in the light curve. So you can measure the rotational period of this little white dwarf hundreds of light years away by carefully monitoring its light curve. So Novae, I talked a bit at the beginning, it looks like a dwarf nova system. The big difference is that the eruption actually is occurring on the surface of the white dwarf. So you have this dwarf nova, it's undergoing its outbursts over and over again. All that matter is draining out of the accretion disk onto the surface of the white dwarf. Well, it can't go anywhere, right? It's at the bottom of this really intense gravitational well. Strong gravity is holding it in place. And so the matter just piles up, outburst after outburst. And eventually, laying there super dense and extremely hot just from the heat of the white dwarf itself, eventually the density and temperature gets high enough that nuclear fusion gets triggered. And because this matter is semi-degenerate, it's compressed to an incredibly high density, that thermonuclear eruption can totally encircle the surface of this white dwarf practically instantaneously. And so you get this huge explosion. You've got this thing that's the size of the Earth, basically, is a good scale. And basically it's like the entire Earth's surface was covered with hydrogen fusion bombs and you ignited them all at once. That's the kind of energy we're talking about here. And so it blows out this massive envelope of gas at very high temperature, expands very rapidly, thousands of kilometers per second. And it's that shell that we see that makes the nova light curve. It's expanding very rapidly as it grows. The surface area gets bigger, so the star gets much brighter very quickly. So we have this really steep climb in the light curve until finally you get to a point where it's slowing down and it's cooling, and that is where the light curve kind of takes the curve downward, and this disk gradually expands and cools, and the nova fades over time, days, maybe weeks, months, years, and really oddballs that we really don't understand. But again, these systems take a very long time, perhaps centuries, to get back to their original state. Recurrent novae are really a subclass of classical novae. Basically, it means here is a nova we have seen reoccur. It's gone into a nova outburst more than once, and U Scorpii goes in outburst about every 10 years, about 100 years is the top end, because that's about the the time of the photographic surveys and things where we had accurate measurements and good sky coverage. That's kind of the time range we're talking about for recurrence of these novae. Regular novae may be on the order of millennia between outbursts. So clearly something's a little different here. These the white dwarfs in these systems tend to be more massive, so they're accreting matter more quickly, or they can draw it out of the accretion disk more quickly. And they're very rare. There's only less than a dozen known in the Milky Way. There is in the Andromeda Galaxy, the most extreme example we know of today is this M31N 2008-12A. Such as the world we live in today with all of these giant surveys that we get these identifiers like this, but at least gives you, it makes sense. N for Nova, M31 for the Messier designation for the Andromeda Galaxy, and 2008 for when it was discovered. This particular star goes into outburst about every year. So 10 times more rapid than the fastest one in our galaxy. So probably we have a very massive white dwarf here with a fairly massive donor in a very close orbit so that it can accumulate matter very quickly. This one, because it's in a nearby galaxy, actually you can detect this with a moderate-sized amateur telescope in the CCD. I got to observe, make a couple of measurements of this last outburst here with my 35 centimeter scope here in a not very good suburban sky in Florida. So definitely within range of a lot of amateur telescopes. And finally, supernovae, not, last but not least by far. These are massive eruptions, right? I can't say that enough. Star increases in brightness by billions in hours. And oftentimes this one star is as bright as all the other stars, the billions, tens of billions, hundreds of billions of stars that are in its host galaxy. It puts out that much energy over its peak time for a few days. And there are two main types. There are really lots of types, but you break them into two major categories. There have been many, many types, usually based on spectroscopic signatures over the years suggested. But type 1A, these are caused by white dwarfs. And it's not clear. There's two competing theories. So this is an area of active research. Either we're talking of two white dwarfs in a binary that merge. They gradually become closer and closer because they're radiating gravitational waves. Very exciting, cutting edge physics here. Until they get close enough that they merge. Or it's a massive white dwarf that's been accumulating matter, perhaps in a recurrent nova. And finally, it reaches that same mass limit of about 1.4 times the sun's mass, at which point the degenerate matter can no longer support the mass, and the gravity's too strong, and it collapses. It's not massive enough to collapse down to, say, a neutron star, and it gets, it's very, very hot. And so that matter falling in very fast in that, massive magnetic or gravitational field bounces back out. And the entire mass of that star is thrown back out at a reasonable fraction of the speed of light. And the star is totally destroyed. This, again, like a nova, they have this expanding shell of matter, only much more massive, much hotter, moving much faster, so we get a much larger light curve, much greater increase in brightness, a factor of billions. And again, as the shell expands, it cools over months, it gradually fades away. The type 2 1Bs, type 2s, these are all, the important part is these are all supergiant stars. 5, 10, 20 times the mass of the sun. They burn their fuel very quickly, millions of years, and they're done. When they run out of fusionable material in their core, that fusion turns off. That 10 masses of 10 solar masses of matter that were being held up by that fusion energy suddenly start falling in on top of the core. And again, like the 1A, it reaches a critical point of temperature and pressure, and that the outer shell gets thrown back out, rebounds, and again forms this massive shell that's expanding out. And depending on the mass of the original star, you might end up with a neutron star or a black hole, or possibly it annihilates itself and there's just nothing left behind. In any event, you probably aren't going to get a recurrent supernova because there's just nothing left. So we talked a lot about the physics, hopefully not too much. I don't hear any snoring, but then I guess you all are muted, so you could all be asleep. Why do we observe cataclysmic variables? Well, I mentioned some different objects. There's lots of things we don't know about them. Some of these systems have parallels with say the supermassive black holes in the cores of galaxies, where we have these, it's obviously accreting matter a lot of the time from surrounding gas clouds, and the intense magnetic or gravitational fields pulling that matter in, and it'll be throwing out jets of energy, which we see more so like in the more energetic X-ray binary systems. But there's these are a good way to study some of these physical processes that apply to supermassive black holes, which we just can't observe nearly as well because they're all far away and they're in the cores of galaxies where it's really hard to observe them. Whereas dwarf novae are sitting out in mostly empty space and oftentimes very nearby. So as astronomers, monitoring outbursts, that's been the bread and butter of the CV section for a very long time. Visual observers, we saw that light curve on SS Cygni. There was a lot of CCD data in there, over the recent years, but the bulk of those 600,000 observations were visual astronomers, making estimates, and that long span of data has been is valuable just because it is such a long span. We have a good idea of what it's doing at least over 100 years. In today's era of massive professional surveys, watching the sky, anything that blinks is getting measured. It seems like maybe there's not so much use, but important thing to remember there is a lot of those surveys are focusing on faint objects. They're on the faint end because they're using these giant telescopes, and a 15th magnitude object is probably too bright for them, right? So things that we can observe with our telescopes are out of range for them to measure reliably. And also a lot of the they're great at detecting new cataclysmic variables, but they aren't detecting anomalous behavior very well. Their data analysis is only as good as what they taught their algorithms to do that they put in their computers. I doubt that anyone is looking in a massive survey right now for like Z-cam behavior, because you gotta know the context of like what has the star been doing over recent time or long spans of time. So searching for Z-cam stars is certainly something you can do from your own data, or mining those surveys. Looking through at the SS Cygni type stars and seeing if there's light curves or showing those kinds of standstills. Dwarf novae are all binary systems, of course. So if the alignment is right, you end up with an eclipse. So that's very interesting because this orbital period is very short, typically 3-4 hours. You can get a couple of eclipses every night. And what's more, because it's really the white dwarf that's the bulk of the energy in the system, and it's very tiny, these eclipses are very fast. So you'll get be a nice normal light curve, and then all of a sudden just a straight drop, 2 or 3 magnitudes. And after just a few minutes, the star will shoot right back up because the white dwarf has popped into view behind the red dwarf. And in addition to that, you've got this accretion disk, which also contributes some light to the system. And it may be getting eclipsed, and it's got hot spots and irregularities. Maybe it's elliptical. And so you get these wings on the eclipse, where it gradually goes into eclipse as the fades, as the more and more of the accretion disk is blocked by the red dwarf. And those look different night to night because of the variations in that accretion disk and in the mass transfer flow. And even in systems that don't eclipse, we can still measure the orbital periods for a lot of these, because there are spots that are hotter. We've got the hot spot in the disk where the matter is streaming down from the companion. And probably more importantly, in a lot of these systems, the white dwarf is so bright, so hot, that it heats up the near hemisphere of the red dwarf. And you can see that signal when the red, the hot side of the red dwarf is pointed towards us. It's a little bit brighter, and 180 degrees later in the orbit, we're seeing the cooler backside of the red dwarf, and so you can measure the orbital period on a lot of systems that way. Along with that, I'd mentioned on the intermediate polars and polars that the rotational period of the white dwarf itself can actually be measured from the observing the signal from those hot spots from the magnetic accretion happening onto the surface. And again, not a way you can't imagine this little thing 8,000 miles in diameter, 500 light years away, and you're able to measure how fast it's rotating. And it's rotating very fast, a matter of several minutes. So you can see a lot of rotations on that in a night. And this is all important. All of these orbital period and rotational periods are important to measure. and because we've got mass transfer going on, angular momentum is being exchanged between the components in the system. So by measuring how the orbital period changes because of this exchange of angular momentum, you can get an idea of how much mass is being transferred between the objects. That's not a week project, that's a many-year project because it's a small effect, but it gives measurements of things that we otherwise have no idea knowing, or no other way to measure, and are important in being able to model these systems. Finally, quickly touch on novae and supernovae. Again, surveys finding a lot of the fainter novae, and surveys finding lots of extragalactic supernovae today. So it's not as wide open as it used to be. There's still a lot of novae being discovered by amateurs, mostly through their own little surveys with DSLRs maybe, and imaging the sky repeatedly. They have one advantage in that the surveys, with their big, expensive telescopes and their giant cameras, and they don't open up till it's totally dark. Whereas amateur survey, you could get out there and observe in the twilight periods. The sky is not quite dark, and maybe catch a novae that they would not have picked up till it moved further into the night sky. Supernova. There's a good chance that an amateur will be the person to first spot the next Milky Way supernova. Sounds exciting, right? We've only been waiting 400 years though. So, don't make that your main observing program, or you'll be probably very disappointed for a very long time. But, we all know the night sky, we're out looking at it. If a -3 magnitude star suddenly popped up in the sky in the twilight hanging there, and you're like, wait a minute, Venus is in the morning sky, what is that? You have a chance at a bit of fame there, plus the excitement of finally getting a supernova in our Milky Way. We're overdue. So I appreciate y'all's attention. Hopefully I wasn't too scratchy voiced through all of this. We'll have a Q&A session at the end, like Stella said. With this, I'm going to turn it over to Dr. Joe Patterson, and he's going to tell you about one of these very successful pro-am programs studying CVs.
Thank you, Sean. And while Joe is sharing his screen, he's getting ready, I would like to actually point out that even the fast Andromeda nova has been, the eruptions every year have been discovered by members of our community, exactly because it's so fast and it's so, it requires such persistent observations. Actually, last year it was Arto Oksanen who discovered the eruption. And it highlights, if not anything else, how key our observer community's contributions are in order to understand those objects. So with that, I'll leave it to Joe. Joe, take it from here.
Okay, thank you very much, Stella. And
Will you share your full screen, please?
say again?
Put it in a full screen mode.
Yeah, hang on a second. Just
okay.
I'm having a little trouble getting this to full screen.
At the very bottom right of your screen.
Yeah.
Keep going down, your cursor. Keep going down. That's up. All right, on your right, there are some icons before the 39%. The icon before it. If you click on that, one more, that one.
Thank you very much, Stella.
Most welcome.
Okay, so thank you, Sean, for that introduction. I'm going to hit a few more specialized points, which cover the some of the recent projects that we've undertaken and to some extent completed at the Center for Backyard Astrophysics. Now, as many of you know, the Center for Backyard Astrophysics is not a particular place. My office is just in New York City, but we're all over the world. And this is a map of the telescopes, almost all of which are amateur telescopes, as they existed about 5 years ago. So it's a little bit out of date. We lost our Hawaii node there when Lou Cook left Hawaii. We picked up a very good South Chilean station when Josh Hampsh established his automated telescope there in Chile, and then it's more or less, and then we have lots of nodes in North America and Europe. Now these are not all active telescopes. After all, these are essentially amateur astronomers. People have day jobs, and and sometimes amateur astronomy is a transient hobby. These people don't have careers in astronomy, so some of these people will contribute data for 2 years, 5 years, 10 years, and then turn to gardening or something like that. So not all of these people are active at any one time. I typically receive something like 5 to 7 or so time series of these stars every night, something like that. And what we typically do, either I or someone else in the network will send out some notes saying, let's concentrate on some particular variable star and try to get data on it all over the world. Of course, the idea really is the original idea was to follow variable stars around the clock. It's always dark somewhere. And so that's what we tried to do. We tried to get coverage all over the globe, north and south. Surprisingly, even though we have far few telescopes in the south, we actually do a little bit better in the south, because in the north we have the wide expanse of the Pacific Ocean, and then we have this sort of Asian gap here, primarily because there's a competitor network in Asia, and I don't know, there's kind of a Great East Asia co-prosperity sphere or something, so they don't, we send much of our data goes to them because they use the AAVSO data, and almost all of our data goes to the AAVSO. We don't get anything back. Anyway, in the southern hemisphere, we have several observers in New Zealand. We have several excellent observers in Eastern Australia. One great observer, Greg Bolt, in Western Australia, and then Bertel Menard in South Africa, who's been observing with us, for some time, for about 25 years. So there are some of the early co-conspirators in our enterprise. The guy on the left tending his 26-inch telescope in his backyard in Greater Washington, D.C. is Dave Skillman. Some of you know him. I think that telescope was built by Jerry Foote, as a matter of fact, which many of you know. And the guy on the far right is Tony van Munster in Belgium. Many of you know him. Probably most of you in Europe probably know him. He's also very well known for his analysis software that he's written. If you want to really study the light curves of cataclysmic variables, you can hardly do better than his Paranzo software, which he has written. And the guy in the center is Jonathan Kemp, who many of you know. He was a Columbia student many years ago, and then worked out at Hawaii at the Maxwell Radio Telescope, and now is runs the observatory at Middlebury College. So all these people are some of the major forces behind the CBA. Some other people here, there's Lou Cook with his 26-inch telescope in East Bay, I believe, San Francisco. I understand observing conditions are a little deteriorated recently. In fact, a letter from Lou arrived recently telling me that Jeff Stone's house actually burned to the ground. Many of you in Western United States know Jeff Stone. I don't know if his observatory did, because his observatory is not with his house, but you might want to write to him if you know him. I think that's Don Starkey's observing room there in Indiana. I don't see Don in there, so I'm not sure, but I'm pretty sure it is. Guy in the upper right is Bob Freed, who was died tragically in a plane crash on a mission of mercy piloted by him about 15 years ago, but ran an observatory in near Flagstaff. I believe that's Mark Boss at the lower left with the University of Auckland telescope. I'm not sure, the one down center below, I'm not really sure which telescope that is. It doesn't really look like a CBA telescope, but not sure. The guy in the lower right is Bertha Menard. Remember, I met him 20 years ago when I spent a year in South Africa, and some of you know him. I got to say, when I met him, I learned why the British could never defeat the Boers in the Boer War. He is one tough guy, and his observations are extremely high quality, and he observes every night in his observatory. Well, so we're the Center for Backyard Astrophysics, and we do a little more than observe cataclysmic variables, but mostly they're cataclysmic variables. And cataclysmic variables, as Sean mentioned, are close binary stars in which the donor star is filling its Roche lobe and transferring matter over to the vicinity of a compact star, which is usually, though not always, a white dwarf. Sometimes it's a neutron star, sometimes it's a black hole. Those things are not commonly called cataclysmic variables, though all the physics, at least for the neutron star, is the same. For the black hole, well, it's some additional physics once you get very, very close to the black hole, and we'll talk about that near the end of this talk. Because this material has a lot of angular momentum, it spirals around in the accretion disk. It takes about a week or so, spirals in, spirals in, spirals in, goes splat on the white dwarf. It heats up the white dwarf, and so these white dwarfs are heated up to some extent by material that falls on them. If the accretion rate is very high, they're heated to a very great extent, and I hope I can get to that near the end of this talk here. And then there's this little bright spot here. This used to be discussed a lot in the CV literature, but not so much anymore because, well, it's really not very important. Essentially it's the shock front where the mass transfer stream strikes the disk, and there's a fair amount of light coming from it, but there's much more interest really in the white dwarf itself and in the binary evolution. Well, of course, we publish papers in scientific journals. Most of our papers, or virtually all of our papers, are joint enterprises because there's a lot of observers and just a relatively small number of authors. I write a bunch of these papers. Enrique de Miguel, a professor of physics in Spain, also writes some of the papers. Gordon Myers is somewhere in this list, writes some of the papers as well, and David Skillman down near the bottom, and perhaps some other people. This particular author, near the end, I'm going to talk about this ultra compact binary AM-CAN-VEN. I believe that's near the end. Is that right? Yeah. So before I talk about that, I'm going to talk about some other projects that we have worked on over the years. Working on a little bit less now than before, but still quite a bit. These are the stars called intermediate polars or DQ Hercules stars. The first one found was DQ Hercules in 1954. It wasn't really recognized as a magnetic white dwarf until 1968, actually. But that's what it is. And so you can see there on near the center there, you can see a basic CV, secondary star, donor star, I'll be using those terms interchangeably, fills its Roche lobe, transfers matter over to the vicinity of accretion disk, to the accretion disk. Material spirals around the accretion disk until the magnetism of the white dwarf becomes too strong because it's close to the white dwarf, and then it latches onto the field lines of the white dwarf and follows the field lines as it plummets to the surface. Near the surface, if you look down below, you see, you see the white dwarf being bombarded with this material, which is now radially accreting because the magnetic field is strong enough to enforce radial accretion flow. And so it creates a big shock right above the surface of the white dwarf. Temperature there rises to 10 to the 8 K, 100 million K, so it emits primarily X-rays. Now, this thing is wheeling around every 71 seconds. So as it wheels around, it illuminates the accretion disk, it illuminates the secondary, and as it illuminates these much cooler structures, lots of optical light comes out too, all at the 71-second period. But one of these sort of standard credentials, which some astronomers require for identification as an intermediate polar, is pulsed X-rays. They shouldn't require that because it just so happens that sometimes the X-ray telescopes are not sensitive enough to pick up the pulsed X-rays, but they are sensitive enough to pick up the optical. So it doesn't really make a whole lot of difference what wavelength it is. If it's pulsed very rapidly, minutes or tens of minutes, it's almost certainly coming from a rapidly spinning white dwarf. Now, in the light curve, in many of these things, you can actually see these things in the light curve. If you look up here, this is FO Aquarii, one of the most famous of these stars. I call it the king of the DQ Hercules stars because there's a very large amplitude. This is a 20% signal in the light, this little rapid thing, every 21 minutes. And excuse me a second there. So it's a large amplitude signal. You can see it in the light curve. When I first saw this back in the early 80s, it was very easy to measure the period because all you have to do is just count the time from one pulse to the next pulse to the next pulse to the next pulse. And I saw that it was 21 minutes. There's also an orbital signal every 4.8 hours, which the arrows indicate. So I spent 15 years studying these stars. I'm still studying them, really, but 15 years where they were the major subject of my research because I was greedy. I realized I could not see these stars all over the sky. Nobody else had, found them. And I had this marvelous machine, the Center for Backyard Astrophysics, for accumulating the data. Most of these stars are pretty bright. They're mostly around 15th magnitude or so, and easy targets for CCD photometry. A lot of other stars. I spent a lot of time on Dwarf Novae as well. I won't talk very much about that, namely on the so-called super humps of Dwarf Novae. And basically, essentially any dwarf nova in the sky, if you sit on it long enough, you will learn the orbital period because you'll see a signal in the light curve. go up and down with the orbital period. And you'll also see another period, whenever it goes into eruption, you'll see another period which is displaced a few percent from the orbital period, almost always more than the orbital period. So if the orbital period is 100 minutes, this other period called a superhump period, typically it's around 103 minutes or so. And the errors are pretty small. It's a moderately coherent process. So it's 3% longer, 3 plus or minus 0.1%. So it's not truly coherent. The orbital period is truly coherent. It doesn't change for millions of years. But this thing is a floppier, is a slightly sloppier period. But it turns out that the amount of the displacement from the orbital period actually can tell you the mass of the secondary star, which is really useful because the secondary star is, generally speaking, not seen in the spectrum or in the light curve. Secondary star is usually an M star, an M dwarf. An M dwarf compared to the accretion disk of a cataclysmic and white dwarf, a cataclysmic variable, is a faint object. So you usually don't see the other star. Sometimes you do, thankfully, but usually don't. And so you have to infer its properties by some of its gravitational properties, which is what produces this 3%. This is, those of you that have engaged in observation of this, this is all very familiar to you. And the Japanese Taiichi Kato's network, VSNet, also familiar to many of you, I'm sure. They're still doing this, so they're sort of the horse's mouth now on this. I kind of stopped myself because basically, to be honest, they all look pretty similar. So I wasn't really sure I was learning a lot. Some of them are 3%, some of them are 5%, some of them are 0.7%. Okay, and turns out that's pretty interesting. Once that number gets below 1%, it means it's a very, very low mass star because it's basically measuring the size of the perturbation on the accretion disk. And with a very low mass secondary is a very mild perturber on the disk. And so, that turns out to be interesting. But anyway, I kind of moved on to some other targets here. Let's see. Oh yeah, so this is more on the super humps. Yeah, so basically, as I observed them studied them over many years, I discovered there are super humps that are on the high frequency side and on the low frequency side. And they are, I called them positive super humps and negative super humps, and that's still the term that people use. And they basically come about because actually they're very similar to the moon in its orbit around the Earth, because the moon is being perturbed, where the moon is the accretion disk, so to speak. There is no disk, of course, it's just the moon. But nevertheless, it's going around the Earth, and the sun is perturbing it. What is the sun? And the angle of the moon to the ecliptic is, the angle of the moon, to the ecliptic is 5 degrees. And so therefore, the sun is perturbing it slightly and causing the orbit to wiggle. It wiggles, it changes its plane with a period of 18, very similar to the Saros period, about 18 years. And it changes its apsidal location with a period of 8.8 years. And so it turns out this numerology is duplicated by the secondary stars in cataclysmic variables. And there's a number of papers written on that, one or two by me, and some other papers in quite a bit of detail by some other people. Once in a while, something that isn't a cataclysmic swims into our telescopic view. This was a quite famous object that we observed back in, I believe it was 2006. It was the first gravitational lens seen in a nearby star. The gravitational lenses that are famous are either are typically in other galaxies or very distant stars in our galaxy. But this was a very, very nearby star, less than a kiloparsec away. And I remember when I saw the first report that there was this bright object in Cassiopeia, and the spectrum of the object didn't change. It went from 12th magnitude up to 7th magnitude with no spectral change whatever. I noticed that that it was on the night of October 31st that this observation was reported, and I thought, is this a Halloween trick or something? How does this happen? And that a star can brighten by 5 magnitudes and not change its spectrum in the slightest. And waited a few more days. It came down absolutely symmetrically around its peak, never changing its spectrum. It's an ordinary A star, about like Vega, main sequence A0 star, just like Vega. And it's came down, and of course, this is the theoretical prediction for a microlens, a gravitational lens. Some low mass object passed within about 0.0001 arc seconds in front of this A0 star, and it caused the light to be lensed, and the magnification in the lens produced this thing. So more of these things have been found now, so it had to happen eventually. Some of you might know Einstein, of course, predicted gravitational lenses. He predicted them in 1936. It was a very interesting story. I wrote an article at Sky and Telescope about this. It's a very interesting story about how it was he published that thing. He didn't want to publish it because he thought it was a ridiculous prediction that that anyone would ever observe a gravitational lens of a star. And he was sort of forced to publish it by an amateur astronomer who insisted that he publish it. So they published it, and of course, the first one wasn't discovered. I believe it was discovered in 1982, I think, with a quasar, because quasars are lensed quite a bit more frequently than stars are. Okay, so that's a very interesting story, nothing to do with cataclysmic variables. So there is a cataclysmic variable near and dear to my heart, the helium binary V803 Cent. It's alleged to be 2 white dwarfs, both helium white dwarfs, orbiting with a period of 43 minutes, if I remember the number exactly, 43 minutes. And it has an outburst period of several hundred days. And in 1997, we arranged, this before the CBA really got going, but we had telescopes in New Zealand, South Africa, and Chile. And we arranged for simultaneous observation. As you can see from the figure, it looks like we caught the main variability here. The main variability is this 23-hour variability, which of course never could have been found by a single site observer because of the period, 23 hours. And turns out, how interesting is this? Well, it was a very interesting discovery. As far as the astrophysics are concerned, not so interesting, I think, because if you actually time this to find out if it's a stable clock, if it's a truly periodic clock, which would make it very fascinating and would contain some very interesting physics, the answer is no, it's not. This is my C diagram. This would be a straight line if it were truly periodic. It's not. It wanders around. So, it's a. Let's see if I can go back up here. So it's more of like a accretion disk. It's more like, you all know the difference between climate and weather. Weather is interesting day to day. Climate is interesting millennium to millennium. Climate is really more interesting. And this is really weather. And that really the super humps, I've come to regard them as Not that these are super humps. These are basically dwarf nova outbursts in a helium binary. Say some more about that near the end. So I haven't been observing this particular star since then, though. I may get back to it. I love these helium stars. Let me say something about evolution here. This is actually single star evolution. A lot of you know this, but I'm just going to go over it just because double star evolution, which I'm going to talk about shortly, is completely different. And it's in the next slide, I think, is double star evolution. But single star evolution, stars collapse out of the interstellar medium, and depending on their mass, they may become planets. Not really stars, but anyway, zip off to the right and become planets. If they're more than about 0.1 solar masses, they go off and become stars. They live in this boarding house which rents rooms by the millions and billions of years. And then after they leave that boarding house, if their mass is under about 0.5 or so solar masses, they go right into the white dwarf graveyard. Now, there are no stars that have gone into it directly because the galaxy is not old enough for 0.5 solar mass stars to have already exhausted hydrogen in their core. So, so this is the theory, and I presume that once the galaxy gets a little older, some stars will actually follow that path. But the more familiar stars are the ones that are a little more massive, namely more massive than around 1 or 1.5 solar masses, and those are have evolved sufficiently quickly to become giants or supergiants, depending on their mass. If their mass is really high after they're finished with this shell burning in the supergiant phase, they may go directly into become black holes. With or without a supernova, we don't know exactly. There's a lot of energy released in the formation of a black hole, so probably with a supernova, but maybe not. Anyway, the ones that we're interested in is, well, we're interested, of course, in the binaries, but then many of these stars have, well, the ones that don't become black holes will become neutron stars or white dwarfs. The masses under 1.4 solar masses, they go down, become members of the white dwarf graveyard. Otherwise, they become neutron stars. So many of you know that, but anyway, there it is in one picture there. What about a cataclysmic variable? Completely different evolution. Here's how they evolve. You start out with a binary with a period of about a year, and the star on your right starts to evolve. It becomes a red giant. And there you can see it becoming a red giant, and then just a little bit later, red giants don't last very long, so it becomes a bigger red giant, and then finally, if it's sufficiently massive, it becomes a very big red giant, and it could actually encroach upon the other star, which is a little yellow dot there. And it starts out with an orbital period of about a year. The second frame has also an orbital period of about a year. But once it engulfs the other star, you now have a relatively low mass star orbiting inside the atmosphere of this relatively high mass star, which could be a supergiant, or it could just be an ordinary red giant. And that's a very dissipative situation, of course. So what happens is, as the yellow star there orbits round and round and round, it dissipates its energy and angular momentum like crazy, and spirals in, spirals in, spirals in. Now, if you're looking at this thing from afar, you really can't see what's happening because, of course, the binary nature of it is hidden by the enveloping star, the originally more massive star. And so it just looks like a mess. The theorists call it a common envelope binary. And there are, every so often a paper appears saying this particular star, and they name it, it's a common envelope binary. Or it just stopped being a common envelope binary. Anyway, there's no real definite signature of a common envelope binary because it's a rather transient process. Estimates for how long it lasts are around 10,000 years. And that's a very short amount of time in any given star. So there's probably some very odd looking red giant stars floating around in the sky that are actually common envelope binaries. And if you wait another 20,000 years, they'll be respectable CVs. But we don't wait an extra 20,000 years. So we have to kind of figure all these things out. And it's the most mysterious phase of binary evolution, and maybe of all stellar evolution. Anyway, it finally comes out, of course, this thing was a red supergiant. At the core of a red supergiant is a white dwarf. And that's really what a red giant is. It's a gigantic envelope around a white dwarf. Initially, a very hot white dwarf, and then cooling. And then by the time the red giant has lost its envelope in the form of a planetary nebula or a stellar wind that comes out of it, now it becomes a rather commonplace thing. It's essentially a white dwarf, relatively massive, let's say, 0.7, or let's call it 1, round numbers, 1 solar mass, and then the original star, or what's left of it after it's been ravaged by this enveloping star, is the donor star, and that star, at least at first, probably exhibits some signs of its perilous journey through this opaque envelope. However, in a short period of time, it just settles down and becomes something like a 0.5 solar mass star. And that is a CV with a period of a few hours. So this is a known, it's known not because anybody has watched this happen, but by looking at the timescales of these various events, it's very much agreed on that that's how CVs originate. Now I'm going to end by talking in a little more detail about one particular study which we're just about to publish. Quite a few people probably on this call are, you're very familiar with this because you've been observing this star for possibly as many as 20 years. This is a real celebrity star. This is originally called HZ29. It was the 29th object in the Humason Wiki catalog. Of course, there were about 100 objects in the Humason Wiki catalog, so nothing special about it until it was found to have a period of variation of 17 minutes. Exact number is 10:51 seconds. Now this is so the 17 minutes for two stars to go around each other and it was a paper written in 1968 saying, hey, maybe this is an orbital period, the 17 minutes. And it turned out that it is an orbital period. And so these are two stars. They're both white dwarfs, or at least they were thought to be white dwarfs until very recently, until a few months ago. Anyway, they're approximately white dwarfs, and they're definitely very small stars. And as this diagram shows, they are the separation between them is really tiny. The whole binary star would fit inside the body of Jupiter. Not the orbit of Jupiter, mind you. This is of course, the scale of the sun's limb here. And that's the size of Jupiter. And you could fit this binary star inside of Jupiter. And that would do a lot of violence to Jupiter, admittedly, but anyway, you could fit it inside of Jupiter. So they're going around each other every 17 minutes. Now, it turns out that, so we've been observing this star. I've been observing this star for 42 years. I started observing this star in graduate school. I got fascinated with this star. Basically, the star was interesting because it promised to be a test of gravitational radiation. That was the original paper in 1972 said, maybe this is the first star in the sky that is powered by gravitational radiation. After all, there's two more or less stellar mass objects going around each other every 17 minutes. that sounds like a GR type of object, doesn't it? And put it that way, they trotted out the argument mathematically, and it turns out to be sort of true and sort of not true. We'll see that in a few minutes. Anyway, after observing it about 20 years or so, I and my colleagues and all the CBA collaborators, we really found these periods out. We discovered the periods very, very exacting. We investigated these periods accurate to about less to better than a millisecond or so. This is an average power spectrum. Some of you are familiar with these things. And this is in cycles per day. So the orbital signal, 1051 seconds, that's sort of buried in here. 1051 seconds is actually not 85.3. There's actually 3 signals buried in this one signal, but because we observed it so long and so assiduously, we found that this actually has a tripartite structure to it. And one of these things is a superhump, a positive superhump. One is a negative superhump. And this turns out, the weakest of all, turns out to be the orbital signal, less than 1/100th of a magnitude. So you can't actually see it in the light curve. You can see 1051. Turns out if you have a telescope maybe 14 inches or bigger, you can observe this star pretty well, actually. And maybe even as small as a 10-inch telescope. And so at around 0.02 magnitudes, you can actually see the wiggles in the light curve. But to really dig out this guy here, you got to have a little bit bigger telescope. But we dug it out, wrote some papers about it in the 1990s. The real test, is this coming up here? Yeah. So the real test for this is, first of all, this is the orbital signal. We observed it very assiduously in 2017. And as you can see on this thing, it has a total amplitude of about 0.01 magnitudes or so. So really weak signal. But if you put enough telescopes, even quite small telescopes, none of these telescopes were big, by the way. The biggest telescope in this campaign was probably a 16-inch telescope. And there are lots that were smaller. So anyway, that's the orbital signal. Pretty good sinusoid, not exact, but pretty good. And because I've been entranced by this star, I've been observing for 40 years. For the first 20, I didn't really know what I was doing. And therefore, there's very few points on the left here. But on the other hand, I never throw anything away. And so the data that goes into these points on the left, pardon me for this here. The data, those 2 points on the left, which turn out to be slightly critical in accumulating the O-C diagram. Some of you know what an O-C diagram is, some of you don't probably. An O-C diagram tells you whether the period is changing. You adopt a test period, and if your test period is exactly right on the money, all of these points are going to be right along the axis right along the 0 axis. They're all going to be flat. If there is a constant period but not equal to your test period, then it will be a straight line, either a straight line sloping up, or a straight line sloping down. But if it curves, it means the period is changing. And the degree of curvature tells you the rate of change of period. That's what I was really hoping to see, because that would be the test for whether the star is governed by gravitational radiation. That is to say, whether the mass transfer in the star is due to the gravitational radiation of 2 roughly stellar mass objects that are orbiting every 17 minutes. And so we found the period, this parabolic fit there, corresponds to a change of period of 17 microseconds per year. So unless you observe for a lot of years, it's a little hard to measure that. But since I never throw anything away, and since we observe it every year, we managed to get that baseline of 40 years. So now we got a little theory behind it. We have to throw in a little theory. So we have these 3 periods. in the upper right there. 10:51 seconds. That period wanders. It's a super hump. Not useful for periods because, like I say, it's weather. It's accretion disk weather. 10:11 seconds, the negative super hump. Same issue, accretion disk weather. 10:28 seconds, stable. It's the orbital period. Orbital period is stable. If the orbital period is changing, then some deep physical process has to be changing it. We know there's an accretion disk because it is mass transfer. It flickers as a spectrum of a disk. So you know there's an accretion disk. If there's an accretion disk, if there's a close binary star with a donor filling the Roche lobe, there's a relationship between period and density, which is shown as follows. And it turns out for this particular thing, we know the secondary star has a density of about 1,000 times the sun's density. So, you know, that's why people thought it was a white dwarf, 1,000 times the sun's density. What else could that be for a white dwarf? But it turns out it isn't actually. People said, well, it's a double white dwarf, and the guess was, if you look at this 1,000 solar density, the guess was it was about a 0.05 solar mass white dwarf and a 1 solar mass white dwarf accreting. Most of the white dwarfs and CVs that are accreting are about 1 solar mass. The highest one known is about maybe 1.2. The lowest is maybe about 0.6. So we're just 1 as a round number. Now, so now it just gets a little technical. I will go over it here. So a white dwarf has the property, unlike normal stars. You know, if the sun loses half a solar mass, it will shrink to about half a solar radius. Basically, main sequence stars obey the relation that the radius is proportional to the mass. So if it loses half its solar mass, it will slowly shrink to 1 solar radius. A white dwarf will do the opposite. The smallest white dwarfs are the most massive. And you can, if you think about what happens just prior to a supernova, supernova happens when a white dwarf is driven over, at least a type 1a supernova, occurs when a supernova is driven over 1.4 solar masses. So that's when the white dwarf gets so small that it now can't resist its gravity anymore and it collapses. White dwarfs obey the opposite mass-radius relation. So that means that the density of the star should go down, and therefore, if it's a white dwarf, the density goes down, and therefore the period should increase because p squared rho is constant. Okay, so that's what I was expecting to see. I was expecting to see a parabola that was curving in the upward direction, but that's not what we see. We see the orbital period decreasing. It's a parabola that sheds water rather than loses water. So can we explain this? Okay, this is my last slide. So GR, if it's GR, what will it do? Now we all, not all of us, but you know, if you read the newspapers, pay attention to, you know, the big news from science in the last, I think 5 years, 4 years maybe. You know about gravitational waves, and you know that these gravitational waves come from in-spiraling black holes, usually, or neutron stars. Well, black holes, neutron stars, white dwarfs, they're all, you know, very, very closely related. They're all compact objects, which you don't think of as transferring matter. You know, you think of them as being like rocks. And sure enough, black holes really are, you know, like rocks. I mean, you can't get any more resistant to extracting matter out of an object than a black hole. Can't be done. So so the analysis of a black hole binary, either a supermassive black hole or massive black hole, any black hole, is that when they go in orbit around each other, they'll definitely spiral in. There's no doubt about it. The period will decrease according to this formula over here. Did I lose my screen entirely? I don't think so. You know. So the period will definitely decrease. It'll spiral in, and we all know, that with these gravitational wave detectors, they spiral in pretty fast. And in the last few seconds or so, they merge, and you get this big burst of gravitational waves. You get some gravitational waves before that, but you get a big burst as they merge. However, the effect of mass transfer is the opposite. Now this is the last piece of physics. Some of you may know that most of the angular momentum in the solar system is in Jupiter and Saturn. Of course, most of the mass is in the sun, but the sun is the separation of the sun's center and the sun's center of gravity and the solar system's center of gravity is very small. So actually, most of the angular momentum is in Jupiter and Saturn. So let's just simplify and say most of it is in Jupiter. Imagine if Jupiter loses matter. Jupiter, a low mass object, loses matter to the sun, a high mass object. It's not going to do that, of course, but let's imagine it does, because this is the essential physics of a low mass object losing matter over to a high mass object. Well, angular momentum has to be conserved. And because it's conserved, and you're basically giving, Jupiter is losing the matter, which is containing, Jupiter's angular momentum. Jupiter has to move farther out because it's losing its angular momentum to the sun, which that's a waste because, the sun doesn't have much angular momentum. And so whenever a low mass object transfers matter to a high mass object, the binary will separate. And if you calculate these numbers out, and I've now used this for I've now normalized this for numbers that are appropriate to a cataclysmic variable, namely an m dot. M dot means dm/dt, the mass transfer rate, of 10 to the minus 9 solar masses, and a donor mass, that would be the equivalent of Jupiter in my analogy, of 0.1 solar masses. The mass transfer rate would be 9.4 times 10 to the minus 16. So looking at these two things, GR causes a spiral in by that number, 3.5 times 10 to the minus 16. Mass transfer causes a spiral out by 9 in the amount of 9.4. So it looks like spiral out wins. But we don't see spiral out. We see spiral in. We see these two stars approaching each other. So it's a problem. GR is wrong, or the Newtonian physics is wrong. Well, they can't both be wrong. So so that's the problem. But all you have to do really is monkey with these numbers that are not well known. We don't know what M2 is accurately. We don't know what M dot is accurately. We know them within factors of 3 or so, which is not too bad, speaking astronomically. But it turns out those factors of 3 make a difference. So in fact, if you just change M2 from 0.1 to 0.2, you get P dot now negative, and you get spiral in this amount over here. That puts you in the ballpark. And then you just change the mass accretion rate by a factor of 2 down to 5 times 10 to the minus 10. You get the correct number. So we do understand, even though everybody expected that all the secondary stars in the AM Kenvin stars are all white dwarfs, because it was basically called, they were called double degenerates or twin degenerates for a long time. Actually, the secondary star, while a very low mass star and a very small star, it's actually not a white dwarf. It actually the radius decreases. It has to decrease because as the period gets shorter, the separation gets shorter, and so the radius has to get shorter in order for it not to go totally unstable. So that's the culmination of my 40 years of work on this star, and I got to say it was pretty exciting to me to wrap it up. And right now I think I'll never observe that star again. I'll never recommend anyone else to do it, but of course, come February, when Canven rolls around the sky again, I know that I'll weaken and probably start observing it again. There's one final thing I want to say. I don't think I have any slides on this. No, I don't. And that is the project we're working on now and have been for a few years. This, depending on the season, of course, we have our favorite projects, but I've become enamored of classical novae recently. And you'll hear about that in a few minutes from Fred Walter, who knows much more about it than I do. But I've gotten very, very sort of down and dirty on recent classical novae, classical novae that have gone off in the last 10 years or so. And so I'm trying to urge CBAers to turn their attentions to classical novae and maybe even try to follow them within, not within, but starting at about maybe 1 year after outbursts, because I'm convinced that the light curves that these things show, when they're still bright, they're still, just 8 or 10 magnitudes or so down from maximum, and therefore, still pretty bright, still maybe 12th magnitude or so, 12th, 13th, 14th, 15th magnitude. There's a lot of old novae in that category. And most of them actually don't have known, quote, quiescent light curves. I don't actually think they are at quiescence, but anyway, so I'm trying to whip up some fervor to observe novae. And novae have become very popular lately, as Fred will probably tell you. They've been popular with Fred for a long time, but other people have warmed to them because they're powerful gamma ray sources and radio sources and so forth. So I'll leave it there and pass the baton to Fred.
Thank you, Joe. You unshare your screen so that Fred can share his. And while Fred's getting ready, I'd like to actually point out that we have campaigns right now on about 5 novae. Novae are some of the most popular objects amongst AAVSORs. The cool thing right now with them is that when they're bright, they can be observed spectroscopically. So individuals with small telescopes and spectrographs on them can actually acquire really very, very valuable data on early stages of the eruption and afterwards while the event is declining. So Fred, I need you to unmute, and it's all yours.
Okay. Hello, everybody. Thank you for the introduction, Joe. We're dealing with novae. Let me share my screen. I just blocked my window there. Share screen. My host has disabled attendee screen sharing. Stella. Okay, thank you. I got it. I think. Okay, good. You should see. Let me get my slideshow up, which means I need to get that window out of the way. Okay, you should all see my title here. New Insights into Novae from High Cadence Photometry. Time is short, so I'll speak fast and type your questions in fast too. This is a review of some stuff I know about novae. I did slip this slide in, even though I said I wasn't going to do it. So what is a nova? Very briefly, it's a perturbation. It's a hiccup in binary star evolution between cataclysmic variable and cataclysmic variable. It starts that way and it goes back to that. There we go. So how do you make a nova? Well, very simple. You take a white dwarf star. Now, a single white dwarf star is probably the most boring star in the sky. They do nothing except cool off for the lifetime, for the age of the galaxy. But once you put into a binary, as you have heard, they become exciting. The white dwarf is the only type of star that can physically explode. So you take a white dwarf star, you add hydrogen to the surface, and you wait. And eventually, you get a thermonuclear bomb. This is an old plot that illustrates basically the theory of what's going on. What's plotted is the ignition mass on the y-axis, how much mass you have to put onto a white dwarf star. What's plotted on the x-axis is the mass accretion rate onto the white dwarf star. And if you multiply mass accretion rate times time, you get the amount of mass that's actually fallen onto the surface of the white dwarf star. Those are the diagonal lines here going from 1 to a billion years. And the more or less horizontal lines are the mass of the white dwarf. And you can use a plot like this basically to say that a typical nova is going to explode every 1,000 or 10,000 or 100,000 years. But once your masses get up to about the Chandrasekhar mass at 1.4 solar masses, and your accretion rates are fairly high, you can have something exploding fairly frequently, like the one in M31 that's going off every year. There are textbook novae. There are very few of them, but here is a textbook nova. It appears very abruptly. It fades away. Its quiescent magnitude is about V of 15. It fades. It forms dust. You see dust both as excess emission in the near infrared and as an absorption in the optical. And in this case, so much dust was formed that it's optically thick in the near infrared as well. So you get this central reversal, even at J, H, and K, and then it just fades away very, very smoothly. And if all novae looked like this, it would be very boring, but they are not. Thing to keep in mind about novae is that you are looking, at least in the optical, at a very small part of a multi-wavelength phenomenon. You are seeing a fireball that is cooling. The visual light is decreasing with time. As the ejecta blown off from the surface of the white dwarf in this thermonuclear explosion become optically thin, you're seeing deeper and deeper into the star, closer to this very, very hot, still nuclear burning white dwarf. And the light that you have been seeing in the optical moves towards ultraviolet wavelengths, and infrared is from dust. If you add up all of this brightness, it's more or less flat. The bolometric luminosity of a nova stays basically constant until all of the hydrogen that's been accreted onto the surface of the white dwarf is burned up. And then it truly fades down towards quiescence. This can take a few days. This can take a few years. This can take a few decades in some cases. It all depends on, well, it depends on a lot. Novae are very important for the galactic ecosystem. They produce much of the lithium in the galaxy. They produce, through nuclear reactions, low, odd-numbered isotopes of carbon, nitrogen, and oxygen. They recycle a lot of stuff into the ISM, not as much as red giants, but more than supernovae because they're much more common. And if you like dust, you can see dust forming. And as was alluded to earlier, as the mass builds up on these white dwarfs over eons, maybe you approach the Chandrasekhar mass and you end up with a type 1a supernova. They're also very complicated. Type 1a supernovae are very simple in comparison. The star explodes. Here, you're dealing with the surface perturbation. There is a second star, therefore there's an axis of symmetry. The viewing angle that you are viewing the system at varies from on the equator to the pole. It makes a big difference. The composition of what falls onto the white dwarf star varies from maybe pure hydrogen up to solar composition or something even more enriched. That affects the explosion. The accretion rate is very, rates differ between systems, and the mass of the white dwarf can be very, very different. And if you're near the Chandrasekhar mass, you get very rapid explosions. You don't eject much matter. And if you have a very low mass white dwarf, you can have explosions that seem to last forever. So they're all very different, which is what makes them, one of the things that makes them interesting. So one of the questions I've been asking, and I don't know the answer to other than as a CV, is what was the progenitor? Does this help us? If we could find the progenitor, would that help us figure out why different novae look different? And if we don't have a time machine, it's really hard to figure out what exploded. Although there are two things that can help us. One is there are 10 known recurrent novae in the galaxy and another few in the Large Magellanic Cloud, and now many in M31. And we know roughly when they will explode. V3890 Sag exploded last year. It goes off, well, about every 29 years. And here's a whole bunch of AAVSO data, wonderful light curve. You'll notice that there's some data from before 20 days before the explosion. I presume the moon was in the way just before the explosion, but so we missed the rise, but the rise is very fast. This is a red giant white dwarf system driven by wind from the red giant. It's much like T-Corbor or RS-OF, other recurrent novae that the AAVSO has accumulated an awful lot of data on. Please keep observing. T-Corbor should go off within the next few years. Or you can get very lucky. A known dwarf nova, V392 Per, exploded in 2018. As far as I can tell, not much was known about V392 Per except that it was a dwarf nova. I haven't found any period, at least in the older literature, but it went up, became 6 magnitude nova, came down. This is all AAVSO data. So we know that CVs, dwarf novae, do explode as regular old novae, and sometimes regular novae turn back into CVs and dwarf novae, as in GK Per or V1047 Sen, which has been an object of interest to some of you in the Southern Hemisphere in the last year or so. Most times you really have to wait for the cataclysmic variable to reappear. This may take years, decades, maybe even millennia in some cases, but we have to look, because we want to know what's going on in there. So I want to give you a couple of examples of what you as observers can do when novae get faint. Now, I'm not going to talk at all about the spectroscopy. I could go on for days about the spectroscopy of these novae. I'm focusing on the photometry because this is what AAVSO mostly does, and which is it's easier for most of you to do as well. So V1369 Sen exploded in 2013, and our TRA went off in 2009. 1369 Sen was a slow nova. Left-hand plot shows the initial decay. It didn't do much for the first month and a half or so, except it's highly variable. It's going up and down by nearly 2 magnitudes on time scales of a week or so. About day 90, it formed dust. You can see a dip in the blue and the visual where the dust is absorbing light from the star. Not much going on in R&I. And then there's an excess in the near infrared because the dust you see thermal emission from the dust that is not along the line of sight. On longer time scales on the right, you can see a fairly smooth decay with time. The fact that the different bands don't line up exactly has to do with the fact that much of the flux is coming from emission lines in the oxygen 3 lines in visual light in V, in green, and in orange, the H alpha and the nitrogen 2 lines are contributing a lot at later times. So this is a slow nova, which attracted my interest because I have altogether too much spectroscopy on it, and there are correlations between the light curve, the optical light curve, and dust formation and ejecta on the line of sight. Anyways, I want to find the underlying cataclysmic variable. I want to know what the period is. The TESS satellite, the Transiting Exoplanet Survey satellite, observed this as it observed most of the southern sky about a year or so ago. And this is the data from TESS, 30-minute integrations for 27 days. There's one purple point there. That's a point that I got using the Andycam Observatory instrument at SMARTS. There were 2 open circles, one here and one here, which are 2 AAVSO points. Those are I-band because TESS observes between 6,000 and 10,000 angstroms. You can actually get a period out of that. You can do some time series analysis and get a period. The amplitude's a couple of percent. It's noisy, but then it's a nova, it's a CV. You expect things to be somewhat noisy. And the period's about 4 hours. I presented a challenge to some of the CV observers at the AAVSO conference in November. And some of you I know were there. And I said, let's go back to this and try to find the period. It's about 13th magnitude in I. It should be doable. And Gordon Myers took me up on it. And this is his data from 4 observing runs. And we have a period of 0.1651 days. The amplitude is larger. The star is fainter. This is about a year after the test data were taken, 8 months after or something. So the star has faded. The emission lines have faded. On the other hand, the period's 5% longer than we get out of tests. I'm going to have to think about that. We may be looking at 2 different things, but there's clearly a period here that is appears to be reproducible. There's one night that seems to have a little offset. I don't know if there's a timing error or what, but this is good data taken by one of your members, one of your colleagues in the AAVSO. Nova TRA, I brought this in because the Center for Backyard Astrophysics contributed to this. This went off a long time ago, 11 years ago. It's a slow nova with multiple peaks, which you can see on the right-hand side. That's all AAVSO data because I didn't start, I think that one black point is mine, but I didn't observe much of it early on. This is a longer term light curve, the AAVSO data sort of give up after the first year. That's the open circles. I took over with Andy Cam, followed it down, and then you might notice that there's a low point here. I've labeled that with a question mark. Is that interesting? I believe that's an eclipse. And once we got to the next observing season, over here, you can see that the star is going up and down by over half a magnitude. Those are clearly eclipses. I told Joe Patterson about this, or I asked him about this, and he put the CBA on it, and he gave me back shortly thereafter 1,970 observations amassed by his people over 34 nights. And this is what you get when you fold the data. You see a very nice ellipsoidal light curve. It looks like an eclipse, maybe a secondary eclipse in there too. It's noisy. This is down around 15th magnitude. These are people with smallish telescopes. But if you add it all together and you take means, the error bars are means in 0.05 cycle bins, and the green is actually the mean. You see a very nice light curve. It's about 5 3/4 hours. We have spectroscopy on this, by the way, we have better. This is the professional photometry. It doesn't really show the secondary, it just shows a lot of noise out there. And we have an ultraviolet dip too from XMM. It's a very broad eclipse in the ultraviolet. We are seeing the eclipse of a hot inner accretion disk, I believe. It's not the eclipse of a white dwarf. White dwarfs are tiny. We have phase resolved spectroscopy. This is a hotter than a nova-like system. It has oxygen 6, carbon 4, nitrogen 5 in emission. In the optical, those are all permitted lines. So we're seeing an accretion disk that has reformed in this 5-hour CV-like system. So tasks for you if you want to take them on. What can you do to help us professionals out when the novae are faint like this? High cadence filter photometry. Let's find periods. The periods are going to be between 1.5 and 6 hours. Sit on it for a whole night and keep doing it. It's an investment in time. Magnitudes are typically between 3 and however faint you can reach. And the goal is to measure periods. As Joe Patterson said, we want to know what the periods are. There's not a lot known about these once they get faint. They may not be all the way back to quiescence, but measuring a period tells you an awful lot about what's going on there. Then there are novae when they're bright. I'm going to pick again on Nova Sen, V1369 Sen, and Nova SCO 2019. There are things we don't understand when novae are bright and easy to observe. They're also varying quickly. This is that light curve I showed you of B1369 Sen. And you can see here at an age of about 10 days, it's going from, magnitude 3.5 down to 5.5 in a few days. And it comes back up and it goes down, it comes back up and it comes back up. And these are some time series taken by AVSO observers. This is the dust tip over here. I want to know what is happening here. Why is the nova not doing what a textbook nova is supposed to do, which is merely fading away? There's something else going on here. There's a lot else going on here. In fact, this is basically nightly spectroscopy of the sodium D lines. The nova exploded at the bottom down here, and the top is about 90 days later, and the interstellar lines are here and here. And what you see is ejecta from the nova here, ejecta from the nova here. Sodium D lines are good because it's a doublet separated by 300 kilometers per second, and you can identify it very easily, unlike single, say, iron 2 lines. There's another doublet that shows up here, 3 distinct ejections of material. That basically happened here and here and here. So there's some correlation between the ejective material and the change in the brightness of the nova. I want to follow that up. That wasn't the only nova that does that. A lot of novae look like that. This is what you get when you look with tests on 30-minute timescales for a month. The overplotted magenta circles are AVSO I-band data. They match very nicely. You can do as well as tests can. You just have to put more effort in to keep observing. But you can see this is varying by nearly a magnitude, 0.8 magnitudes or so. Time scales of about 10 days from peak to peak. I don't have as much spectroscopy on this one, but I want to find one like this in the spring and enlist a bunch of you to get the photometry, and I'll get the spectroscopy, and we'll try to figure out how the nova loses its mass. So when novae are bright, high cadence filter photometry. We want filter photometry because I want to see how the colors are changing, and I'll try to get the simultaneous high dispersion spectroscopy. These can be 3rd magnitude, they can be 12th magnitude, they can be anywhere in between, and you want to observe them frequently for weeks to a month or two, because novae all change on their own time scale, not our time scales. Finally, there is a middle ground between novae being bright and novae being faint. Not all novae decay smoothly. Like, the ones I've shown you have decayed smoothly. Some get stuck. Maybe it's like the Z-Cam stars. I don't know, but these get stuck. V1280 SCO is one of them. It's the best example. It was a perfectly normal dust-forming nova. It got to magnitude 3.8. I think it's still the brightest optical nova of the millennium, but I may be wrong. Here's the light curve. This is partly my data, partly AVSO, but it all gets sort of stuck together in here. And it's it started out about 16th magnitude, got up to 3rd, dust dip, came down, and it stabilized at about 10th magnitude, 6 magnitudes, 7 magnitudes above quiescence. Novae are not supposed to do this. And then a couple of years ago, it started dipping by a magnitude and coming back. And I think, this shows AVSO data through one of these dips. It's sitting around here at V of about 10.6, and all of a sudden it drops. And it drops down by about half a magnitude. It does that in a colorless fashion. It does that in all bands, and it stayed low for a while, and it's since come back. It's still bouncing around between 10 and 11. It's not going down to 16. I don't know why. I'm not going to show you the spectra, of which I could talk for hours. It's a cool spectrum dominated by lines of iron 2 with a strong helium wind, and near as I can tell, it's a melting Dyson sphere, but don't tell anybody I told you that. This is what Tess saw when Tess looked at it. Ground-based I-band data are overplotted in open circles for AVSO data and filled circles for my data. They match very nicely, but you can see this thing is going up and down by 1/10 of a magnitude or so on time scales of a night. So this is a project for somebody who just wants to sit on it and observe it all night, night after night, to see what it is doing. It looks like this almost periodic on a time scale of 13.5 days, but given 1.5 periods, I wouldn't stick my head out and say that. But, you know, with ground-based data, maybe you can say that. But it'll take a long-term investment. But this is varying on short time scales and long time scales of weeks. So when the novae get stuck like this one, we need long-term filter photometry, long-term monitoring. Again, colors are important, but visual monitoring is important too. This is at about the 11th magnitude. I want to know when this is going to drop to 16th or 17th magnitude, when whatever it's doing now is going to end. For that, I don't need accurate photometry. An eyeball should be able to do it. This is stuck at 10th magnitude. Time scales are hours to years. And I just want to learn, why is this so peculiar? So finally, just to reiterate, how can you contribute to Nova Science? You can do the photometry. Professional astronomers don't get time to do photometry like this anymore. You have the ability to invest, if you have the time, to get this long-term high cadence photometry, and that can really help us out. So please, please keep observing. Usual acknowledgements, and I will stop with that. So thank you for your attention.
Awesome. I'm pretty sure we can actually sit here for hours and talk about cataclysmic variables. They're such fascinating objects, and the mess part actually could be resolved just with discussion and modeling. I would like to share my screen for a second here and remind you all that you can find a lot of information on the AAVSO observing section, the CV observing section. This is a snapshot of this. What you can find here is information about the cataclysmic variables, what they are, how they work, what the light curves can tell us. Just keep scrolling down. You can find information on how you can actually join this observing section and be part of the discussion. People were asking on the chat about targets. You can find our target list here. So these are stars that we recommend to be observed. And if Joe or Fred or any of our friends or Sean want their own stars being observed, they will ask for them. They're going to be on the CV target list. You can also find a group of resources there, one of which is our forum. Since we don't have time to go to questions here today, I would like to encourage you to go to our forums and ask questions there and continue the conversation. You can find also a link to CBA. So all the information that Joe Patterson has on his group is there, and also some information for beginners. If you just started the CVs, this is actually going to be a really good link for you. We're reaching the end. I would like to remind you the recording of this and of all our webinars will appear on the AAVSO's YouTube channel, so please subscribe and follow us there. At the very end of this webinar, before you leave, you're going to receive a survey, so please give us feedback through the survey. Please, please, please remember to renew your membership. You can actually renew now for 2021 and consider supporting the AAVSO with a donation. Your donations enable us to bring you programs like this webinar, and we would like to continue in 2021 as well. Thank you again to Boyce, Astro, and Commerce who support this webinar, and thanks from the bottom of my heart to our CV section leaders and our speakers, Sean Dvorak, and Patrick Schmier, our observing section leaders, Fred Walter and Joe Patterson, our visiting astronomers for today and speakers. And for all of you, reminding you that next Saturday we will talk about telescopes and equipment. So sign up and join us. I hope to see you there. Goodbye, stay safe, and talk to you soon. Bye.
All right.
Start.